There's a question that keeps coming up whenever fructose is discussed, and it usually sounds like this. If fructose is so harmful, then why does nature use it everywhere? Because hummingbirds use it, bears use it, migratory birds depend on it, desert animals survive on it, creatures that live without oxygen rely on it. And that's not a coincidence and it's not a mistake. But the reason why takes a minute to see. When biology invents something once, it might be accidental, but when the same solution shows up across species, across climates, across survival pressures, it becomes a fingerprint. And fructose metabolism is one of those fingerprints. It only appears when survival is uncertain. So let's start with an example that looks most like us. Hummingbirds. Hummingbirds live on the edge of metabolism. By day, they consume enormous amounts of sugar, often close to their own body weight, and blood glucose rises to levels that we would call diabetic in humans, but they aren't sick. They burn sugar directly in flight. Their wings beat dozens of times per second, and energy is spent immediately. And then night comes, and they stop eating and they switch to fat. Body temperature drops, metabolism slows, and many species enter torpor, a deep energy-saving state. And by morning, that entire diabetic state is gone. And that's crucial. Hummingbirds basically show us that fructose metabolism isn't inherently pathological. It's powerful, and it's meant to be temporary. They show daily activation and daily recovery. Humans mimic that daytime half beautifully, but we rarely engage the reset. Now let's move to a more familiar animal, bears. Every fall, bears do something that looks metabolically reckless. They gorge on berries, they spike their insulin, they rapidly gain fat, and they slow their metabolism. And it's exactly what modern nutrition tells us not to do. But it's not indulgence, it's preparation. Fructose acts as a seasonal signal. Abundance now because scarcity is coming soon. And so fat is stored aggressively. Hunger rises. Energy expenditure falls. And here's the part that most people miss. Bear reproduction is directly tied to this switch because fertilized eggs don't implant unless fat reserves are sufficient. And so if energy stores fall, pregnancy is aborted because survival always comes first. In bears, fructose isn't about sweetness. It's like a countdown timer. Now take to the sky. Consider the bar-tailed godwit, which migrates from Alaska to New Zealand, over 11,000 kilometers nonstop. No food, no water. Before departure, these birds enter a feeding phase. They consume carbohydrate-rich foods, including berries and starches, and their liver fat increases. Their muscle mass shrinks even to reduce oxygen demand. And it's not just calorie loading. Fructose metabolism ramps up before takeoff, and then their flight begins. And as dehydration sets in, the polyol pathway activates internally. Glucose is converted into fructose. Fat is burned. Metabolic water is produced. Energy use slows just enough to stretch those reserves. So fructose metabolism is triggered twice. By diet before flight, and then by dehydration during flight. Different inputs, but the same pathway. And the point is, they arrive alive. Now remove sugar entirely. Let's go to the desert. Camels don't store fat in their humps for decoration. That hump is a canteen. Because when water is scarce, dehydration itself activates fructose metabolism via the polyol pathway. Glucose is converted internally into fructose. Uric acid rises, mitochondrial energy production slows, and fat oxidation produces metabolic water. The camel doesn't need sugar to flip the switch. Dehydration alone is enough. Again, different trigger, but same outcome. Conserve water, conserve energy, and survive the drought. Now let's shift perspective. Reptiles aren't heavy fructose users in the same way mammals are, but they reveal something essential. Most reptiles excrete nitrogen as uric acid, not urea. Uric acid is thick. It's semi-solid. It wastes basically no water. That's not inefficient biology. It's conservation biology. Now, in mammals, uric acid amplifies fructose metabolism. It suppresses nitric oxide, and it slows mitochondrial energy output. Reptiles built the conservation strategy directly into their waste handling. They don't need fructose to get the same effect. It's different wiring, but it's the same result. They preserve water, they slow metabolism, and that enables them to survive arid environments. Same ingredients, but different implementation. Now let's remove food and water entirely and go underground. Naked mole rats live in crowded tunnels with dangerously low oxygen levels. Under conditions that would damage a human brain in minutes, they survive by switching fuel use. They rely on fructose metabolism because fructose can be processed without oxygen. The brain stays alive, the heart keeps beating, and fructose buys them time. In humans, hypoxia from sleep apnea, obesity, or poor circulation activates that same internal program, but instead of rescuing us briefly, it becomes chronic. And again, the problem isn't the mechanism, it's the duration. Let's briefly consider penguins. During breeding and molting, emperor penguins fast for weeks to months in extreme cold. They have no food, no water, they have constant energy loss, and fat becomes their dominant fuel. Insulin drops, uric acid rises, and energy is tightly regulated to preserve heat and survival. And so fructose isn't the entry point here, but conservation is still the goal, and the theme holds up once again. Now let's bring it home to us, humans. Let's start with alcohol. New research now mechanistically resolves that alcohol results in fructose metabolism. The parallels between sugar and alcohol were there for decades, but now it's actually confirmed. Both rapidly deplete ATP, raise uric acid, increase oxidative stress, and suppress mitochondrial energy production. And in nature, this makes sense. Overripe fruit appears late in the season. It contains both fructose and ethanol. And the message is clear: abundance now because scarcity is coming soon. And so it activates energy storage. In humans, alcohol presses this switch year-round without that seasonal off-ramp, which explains why alcohol reliably promotes fat gain, insulin resistance, and fatty liver even without excess calories. Now, humans didn't just inherit this same survival system. We actually run a more sensitive version. We lost the uricase enzyme, so damaging uric acid accumulates in us more easily. We also lost the ability to synthesize vitamin C, increasing our oxidative stress. And then we engineered an environment that presses every one of those survival triggers at once. We have sugar constantly. We have refined carbohydrates that generate fructose internally. We have easy access to alcohol. We have salt, and we increase mild dehydration. We have chronic stress, including low oxygen at night from sleep apnea, which means we didn't just activate the survival switch, we stacked all the inputs. We recreated famine, drought, and hypoxia, all within abundance. So what have we learned? Across species, across ecosystems, across completely different biologies, whenever survival requires conserving energy, conserving water, surviving low oxygen, preparing for uncertainty, fructose metabolism or its biochemical partners appear. It's elegant, it's reliable, and it works until it never turns off. The problem in humans isn't the fructose itself. It's that we built ourselves a world where every survival signal is active at once, all the time. And in doing so, We broke nature's elegant timing. In the next episode, we're going to look at fruit itself and why whole fruit usually isn't the villain, but how nature packaged fructose with built-in brakes and how stripping those safeguards changed everything. Because once you see that pattern, the metabolic crisis stops looking confusing and it starts looking inevitable.